Now, if we have, if the bed is moving, so this time the flow will be from left to right. So I need to explain before moving to the film. Here we have the same bed, 6 mm here it is. We have a flow, but we are above threshold, which is here is 0.07. Well, we have a flow rate of about 6 beats per second, 6 millibeats. And then at t=0, we inject, but here, exactly here, in the frame of U frame, we inject a smaller beat, but 4 mm, so the ratio is only 1.5. And now, because you have movement, you will have holes at the surface here, and you normally small particles, some small particles, some will of course go downstream of this frame, but in the frame, some will infiltrate in fact, we put a small amount of 4 milliliters. So that it's only maybe 2 or 3% of the total, because it's 4 milliliters. So in mass, it's a small percentage. So that the equilibrium was not touched. The equilibrium was not moved. The film is very fast. It's 1 hour maximums in 30 seconds or something like that. Okay. Let's see. Yeah. It's 1 hour. And so notice the building of the small lead transparent layers. Yeah.
May I ask something?
Yeah, sure.
Why does it start to build downstream? I mean, is it because there's the wall is stopping the flow of particles, or just because it's a natural process? I mean, I remember from the fluid at the end.
Yeah. If we don't have a stopper, we don't have a bed.
There is still like a little wall.
Yeah, wall.
That's what's stopping the particles and creating a build-up.
Yeah.
Okay.
Yeah.
Otherwise, they will keep on flowing downstream, and this is
yeah, and you will not have in fact, the problem is that yeah, it will not be possible to have something uniform. I think probably we can talk about this afterwards. So yeah, typically it is typically the kind of thing. What we were looking, especially we were interested especially by when varying flow conditions at segment rate quantity, and also the slope were interesting by the penetration depth here. Because on average, when we did several experiments here, we have several penetration. Well, it is related to the segregation, to the shear stress here, but it is also related can be related to other things. In fact, there is no, I may be mistaken, but I've been told that there is no theory which will give you the penetration here. I'm just moving, as we have little time, sorry. Again, but just to see you. Yeah. It's 1 hour time, 1 hour time videos. Initially there are some clusters, as you can see here and so on. And then there is it's interesting to have segregation rate, but there is also kind of shearing or pushing of particles. Okay, just to illustrate. It's just a slide to illustrate that we are still working a lot on image analysis with the lab University of Saint-Etienne, and big work involved. It was not so easy to have a velocity of 4 order of magnitude. Just to illustrate that we were able to have wave particles. We have trajectories and so velocity and so on. It's a skip because maybe not. Yeah, the last slide on this kinetic sealing, because it was mentioned this morning, one of the theory which exists is this theory of Savage and Moon, relating, actually, it is just to illustrate, it is qualitative, it's to illustrate, it is the gradient of the velocity. If you have the velocity profile, which is exponential, the derivative, which is the shear rate, is also exponential here, okay? And this is an estimation, but a poor estimation. Actually, we're still working on this on the normal velocity. So the little bits, the 4 little bits, that calculate, and we can look at the velocity of the vertical velocity, which is very small, of the order of 10 minus 4, and we can actually try to relate this to the velocity. But it is work in progress.
So is the pink line the measured normal velocity?
Yeah, this is the measurement of normal velocity. Although this curve, the measurement are false. It's just qualitative. But it's the order of magnitude is okay. It's about 10 minus 4, and yeah. I would like to try to relate the vertical velocity, or the normal velocity, to the shear rate.
The normal velocity, is that one of the complements that's like a segregation velocity? Is that what you're...
Yeah.
Segregation velocity, like the large particles up.
It's not the flux, it's the velocity here. It's not the... okay. Now, so we had spontaneous population. It was just to illustrate. We had this kinetic sealing stuff. Now we've done experiments with all kinds of grain size ratio and all kinds of fine feed. Well, you have both. You have both. You have spontaneous population, you have kinetic sealing. So this is another experiment. This is a PhD of Ashley Dodin, close to with my church. And we here the flow will be from right to left. Sorry. And we made a tremendous move. We enlarged the channel from 6.5 millimeter to 10.3 millimeter. This was a cultural upgrade. And so we have now 5 millimeter transform beats.
Still 10% slope.
Still 10% slope. Sorry, I'm stuck at 10%. And you have here, okay, some value, she is 0.009, you have 5 millimeter. And I'm going to illustrate, we're going to feed this fine segment, 0.7 millimeter segment. And the fine feed will be 23% of the total, which is about 10 kilogram per hour. We have 8 kilogram per hour, 5 millimeter beads, constant feed, and we have about something like 2.3 kilogram per hour. These experiments were inspired by, I think Bill, you know quite well these experiments by Isaiah and Slim participated and also. Well, it was a big source of inspiration. But here, everything is fixed except that we will vary. In fact, the grain size ratio here and the fine feed infiltration. But we never vary the flow rate, which will remain this value, and we never vary the coarse settling rate. And here it is, I think it's accelerated 50 times, but you will see that it begins to infiltrate. Okay. And we have to imagine the stopper here, or maybe here, and then it will degrade. After about 15 minutes or so, after 5 minutes it degrades, and then after about 15 minutes, the total film is something like 20 minutes or 30 minutes, and this is the end. It will degrade from about a slope of 10% to a slope of 7%. Okay? So we're adding fine materials. We are at the beginning, okay, with the course, adding fine materials, and everybody knows that in certain circumstances that we would like to investigate, of course, the mixture has a better efficiency. So that actually, to remain at 10%, we should have lowered the flow rate, but we remain at the same flow rate, and then because a lot of energy system, it degrades. So this is 5 and 0.7 millimeter. Okay. Now we do the same, but we use 3 millimeter beads. Okay. 3 millimeter beads, which are actually blue, so that they will oh, sorry. Tack. Yes. And so in this case, for this ratio, there is absolutely no possibility of spontaneous speculation. In this case, you will have an aggregation. Okay. In this case, you will have an aggregation. I have this kind of layer. Then, in fact, there is an aggregation up to 12%, from 10 to 12. Okay. Now, I want to show you the influence of fine feed concentration. So we'll return to 5.07 millimeter, but with a fine feed of 68%. The fine feed is is now higher than the coarser feed. Maybe 2 times, maybe, because it's 68% of the total. Okay, so it's maybe 16 kilogram per hour of fine feed. Of course, it infiltrates much more rapidly. And the layer seems to be, and there is very low concentration, and the beads are just dashing around. They're dashing very fast. So this is work in progress. But we did this, Ashley did this. It's actually a PhD, which is a joint agreement between University of Cornell and University of British Columbia. So she spent 1 year in our lab, and she did this for several grain size ratio from 0.7 to 4. So it is about 1.5 to about 7, the grain size ratio, and with different concentration of fine feed. And what you can see is that, okay, above 3, between 2 or 3, we don't know if there is an aggregation. But also, when we what is interesting, when we increase the fine feed, actually, for low grain size ratio, it again aggravates. First degrades, for example, for 2 millimeter here, first degrade, and then here we have a point where it aggravates. Same for 1.5. For 0.9, it just you have above 50% here of fine feed, 50% of the total. Okay, it again aggravates. So
you're going to tell us why later?
Tell us why.
You're going to tell us why later?
Only partially, because I don't know yet. This is the big problem. So, sorry, 5 minutes. Okay, I will try. This is fresh from the oven. This last week. In fact, with the 5 and 0.7 millimeter, I have problems to detect the beads because it's 0.7 millimeter. Anyway, I did it with 5 and 2 millimeter. Okay, I want to contrast low feed, medium feed, and high feed. So here I have a snapshot. Okay. This is a very busy graphic, but I have six graphics on it. Remember that the flow is from right to left. So here I have negative value for the particle velocity. Here I have a depth profile. This one here is the depth profile, okay, of velocity. And this here, sorry, and this here is the concentration. But in this case, we have some trains starting and stopping, rolling trains, and above these small beams here. But these beams here, they are very rare, but they are very high velocity. It is here, you see? So that in effect, the flux, I have two peaks of flux, which are more or less 50-50, okay? By contrast, if I augment the fine field here, then we have the blue curve. I have only one layer, more or less, of beads. I put the zero more or less at the upper part of the fine layer, okay? The zero elevation, this elevation, okay? And so here I have the concentration here of those beads here, and I have here the velocity, okay? Here the velocity, the black velocity was not that different when you have a uniform case with a kind of exponential increase. Okay? Here we have at zero we have a non-zero velocity, a quite already fair velocity, and this kind of profile. Okay. Then I want to contrast this case, the 2 mm. Remember that for 2 mm at 40% field we have a degradation, about 8%, and we have a malgradation at 68%. If you augment the field, then there is malgradation again. And what is funny, so you have to contrast between the blue and the red. This is the blue and this is the red. We have the same kind of profile. I mean, this is the concentration, or the solid fraction if you prefer, okay? And this is the velocity profile for the 41%, and here from the, of course, you have a much higher velocity, but between the degradation and the aggradation, the depth profiles typically are not that different. Okay. Whereas between the very low fine field and the high fine field, it's different. Okay, conclusion: two sides are experiments. Well, about depth profiles, the pessimistic view is that okay, the profile is what you see, is what you can see by eye. Okay, and so I don't know yet why it behaves so in this way. Because the optimistic view is that because we have these depth profiles, I think that we will try to for example, try to find a theory or relating these profiles to some parameters. I will finish now. Sorry, I will take a few more minutes about what we've done, because this was about modeling, so I mainly presented experimental results. But now I want to do about discrete element model. I thought that Kimberly would present more details, the principle and of discrete element model, which is very popular in granular physics and also in soil mechanics. But because we have typically these experiments at the particle scale, it's quite normal and to try to model this with discrete element modeling. Basically, discrete element modeling is simple, in quotes of course, because it's very simple mechanistic law that you use actually. You use appropriate contact laws. What is very interesting, we use a simple law that the one which Kimberly presented, which is called spring dashpot. What is interesting, it actually defines an effective restitution coefficient and a friction coefficient. And in fact, the results in the model doesn't depend a lot of the value you take for the restitution coefficient and friction coefficient, except the extreme of 0 and 1, of course. So this is why it is popular, this kind of modeling. It has not a big predictive power, this kind of models, but it allows to do numerical experiments. For example, so what we did is something more. We use discrete model and we couple it with a fluid discrete element model. A simple one. We wanted to know what is the simplest model. So we use the 1D Reynolds average Navier-Stokes models with a concentration dependent mixing length. Okay, so not a big, DNS or a very big CFM model, okay? And